In this second video, I want to build up an intuitive understanding of how machine learning models actually learn things. And AI systems, which is built upon machine learning, is fueled by data, oftentimes lots of it. And so there are some parallels here to how we as humans learn things. We learn things from examples. So we're going to dive into that. So from a young age, we learn things by mimicking others. We see other people do things. We hear them talking, how they talk, what they talk about. Oftentimes we replicate that behavior. If you fast forward, software engineers, oftentimes the way that software engineers learn things is they want to see an example. If they're using a new library or API, show me some code that uses that capability. Oftentimes what people will do is they'll copy and paste that sample code and then modify it for their particular use case or their requirements. Sometimes they don't even understand fully what's going on underneath the covers, and that's why I say here there's kind of a copy, paste, modify pattern going on. But the example helps us get started. That's how we can quickly get going, and then as we work with things over time, we gain a better understanding ourselves. So machines and machine learning models, there are some similarities here. So they are trained, what we're going to learn about in this course. One of the main techniques is supervised learning. So we're giving the model examples of questions and answers, or input variables, or what we're going to learn are called features, and then the output or the correct answer. And that could be a numeric value. It could be a classification, such as an email is spam or it's not spam. Lots of different types of use cases that we're going to look at. And in this process, the model is learning patterns from that data, and we're going to train it to arrive at the correct answer. So it's going to learn patterns, not explicit rules that we would be coding, but it's going to pick up these patterns. And so when it does this generalization, sometimes it's going to be wrong as well. We're going to learn about error rates and understand where they come from, how to reduce them, how oftentimes you cannot get rid of them. Most of the times you can't get rid of them completely. And also talk about correlation and causation. So machine learning models, AI is built around primarily correlation. And so the models may not necessarily understand why a given input leads to a particular answer, but oftentimes it will know what the right answer is. And so we'll dig into that as well. Let's start though by thinking about, if you're going to learn a new task, we can model it as a function. So computers are based on math, and even we'll see in language models, what we first have to do is convert those words from a prompt into a numeric representation, because really all of these things are really based on mathematical models. At the end of the day, computers are based on binary zeros and ones that we abstract up into larger numbers, and then eventually words, images, video, etc. But at the core of it, it's math going on. So it's helpful to think of these problems as some function f, where this could be, any function could be predicting what the temperature of the weather is going to be at 2 p.m. It could be predicting how many points your favorite team is going to score in their game tonight, whatever that might be. And so we use the capital letter X. The capital letter indicates that it's more than one thing. It's a set of things. And so we show here there's X1 through Xn, and those are your input features. And so given that, we want to predict or know what the output is. And in general, we can think of this also as a transformation. We're transforming some data coming in, represented by X, and we want some particular data to come out. So keep that in mind as we go. That's going to be an important thing to remember, especially when we get into models like neural networks, which really are transforming very high dimensional data into some answers or outputs that we want to see from it. So in order to build up an intuitive sense of what's going on, let's start with something simple. So our function f, we're going to estimate the height of a person that we're going to encounter. And so let's say initially we don't know anything, right? We haven't measured, we don't know anybody's height. So me personally, I happen to be 5'10". That just happens to be the average male height in the United States. And so we're going to start off with that initial guess. So our function, no matter what input came in, our function f would return 5'10". So let's start there. Here I've just recapped what we talked about. So our model predicting 5'10", 178 centimeters. But now we meet Alex. Alex is 6 foot. So if our model predicts 178 centimeters, we're going to be 5 centimeters off when we predict that for Alex. So what should we do? Should we change our prediction to be 183, do we know if Alex is representative or not of the rest of the population that we're going to run into? We don't really know yet, but for the moment, let's just go ahead and change our model to return 183. So next we meet Bella. So Bella is 5'6", which happens to be 168 centimeters. So if we had predicted 183, Bella's actually 168. Now our error is 15 centimeters. So now we've increased our error rate. Now, keep in mind at this point, we don't know anything about the person. We're just predicting. But as you can see, as we take each new sample, we are adjusting our estimate and we're kind of swinging back and forth, and we're getting a different error rate on each different occurrence that we try to predict. So at this point, we can make a couple observations already. One, we have very few samples, so we don't have enough to get a sense of the actual data distribution. So we're going to be very inaccurate. But also we can see that if we overreact to each individual sample, we end up moving our prediction a lot, and we kind of just bobble around and don't really hone in or converge on a better estimate. So the first thing we can do is say, okay, we're off by 15 centimeters here. So rather than adjust our prediction by the full 15 centimeters, let's nudge the model in the direction of the newest example that we learned about. So rather, let's say 20%. And in machine learning, this is called the learning rate. So our error is 15, so 20% of that would be 3 centimeters. So instead of predicting 183, let's go down by 3. So that would move us to 180 centimeters. So now that's our new prediction. Another lesson that we can learn at this point is that the order that the data comes in can also have a big effect on what our model is going to do, what adjustments it's going to make. So in order to make that more stable, we can take a number of samples at the same time and consider those. So let's say we take 2 people at a time, and this in machine learning is called a batch. So our batch size is 2. So we started with myself at 178 centimeters. That was our initial estimate. Alex and Bella, you see their numbers here. So taking them together as a batch, we can average out their height. And you can see here that's 351 divided by 2, so 175.5. So now if you look at from this first batch that we're running, if we averaged out our new samples, we had predicted 178. Our new batch is actually 175.5. So our error rate is now, or error amount is 2.5. Okay. So instead of adjusting that whole amount, we're going to use our learning rates. So we would adjust by 20% of 2.5, which is actually 0.5. So in this case, we would just lower our estimate by really half a centimeter. So, and that kind of averages out to those 2 other samples that we saw. So batching is an important concept. It helps training become more efficient, and it also helps adjust for variations in the data, and we're not as sensitive to what order everything comes in. Stepping back for a moment, the true function f is the real world, and it would tell you the height of every single person on the planet. So that's obviously not what we're trying to do. We're trying to estimate that, and oftentimes that is denoted by this little hat symbol. So f hat, we're trying to create a function that estimates the real world, and we want it to be as accurate as possible. In order to do that, we need more data and more information about our subjects or samples. So here's an example of data about different people, and we've added 2 features, so age and gender. Already we're seeing different types of data. So age is a numeric value, it's ordinal. Gender is what we call categorical, so it's one thing or the other, and so that gives us more information to help predict our answer. It does actually turn out, age does make a difference. Here you can see a chart. So when we're first born, obviously we're quite short, but even then as we get older, people tend to get a little bit shorter. So this is just a few examples of how features are going to help make our model much more accurate. Now, going back to our model here. So we are not going to take the data from the entire world's population. We're going to take data from some subset of people and use that. And what we're trying to do is use that as a representative set of examples. And if that is independently drawn, then we can make some assumptions and say, okay, well, that reflects the probability, or I should say that reflects the data distribution of everyone's height based on these different characteristics. And that's how we can improve the accuracy of our model. Let's recap now what we talked about. We started in our model with a very simple guess That was our starting point. Then we gradually made adjustments to that. So we nudged our model in the direction of the correct answers as we saw new samples. And instead of just taking one at a time, we kind of grouped them into batches and collectively considered how far off we are with that batch. And by doing that, we stabilized our training a little bit, made our model a little more consistent. And then we looked at what other features, what information can we use to better predict our answer. So these are all key steps in machine learning. Now, we've been talking a lot about distribution. So we're taking a sample of the data, right? We didn't take the height of everybody in the world. We just took some subset, and we wanted that to reflect the entire distribution. So our sample distribution is important because if that's independent and randomly drawn, so randomness is a key here, then we can make some assumptions. Now, if you don't know much else about the data, many things follow what's shown here, normal or Gaussian distribution, where most of the data falls in the middle, cluster around the average or the mean, and then it kind of tapers off after that. The different lines that you see here, so if you consider how far every value is from the average and you take the square of that, we do the square because some values will be positive, some will be negative. So you want to get more of the absolute difference. If you take the square of all of those differences, that's what's called the variance. And then if you take the square root of that, you get the standard deviation. So standard deviation you can think of as kind of like what's a normal difference from the average for each of these values. And you can see within one standard deviation in this dark blue area, you've got 68% of the values all fall within one standard deviation. And then they get much more tapered off after that. So a lot of times the data will follow this kind of pattern, and then that helps us make some assumptions about it. This is not the only distribution, but it is a very common one. Another distribution would be the uniform distribution. So in this case, every possible value has an equally likely chance. So if you roll a fair six-sided die, this graph shows you that 1 through 6, they've all got an equal chance, 1 in 6, of coming up and being the value. Now, if you roll 2 dice and you're considering what the total will be, now your probability distribution is going to look more like this, because 7 is the most probable value because there are more combinations of numbers that will add up to 7. And of course, going all the way out to the edges, so 2, there's only a 1 and a 1. 12, there's only a 6 and a 6, much lower probability of getting those. So this chart here shows some common distributions. We've already talked about normal and uniform, and you'll see there's a difference here. So binomial and Poisson have these bar chart, it's like a bar chart basically. So those work with discrete probabilities. So if you were talking about what's the temperature going to be tomorrow, you might get a normal distribution based on the time of year. But if you're talking about the total of rolling 2 dice, you might get something like binomial because those are discrete possibilities. The other thing you can do is if you have a continuous value, you can narrow that down into different bins. But these are some of the common distributions that we'll end up encountering. So as I mentioned, you have these 2 types of data, numerical and categorical. Numerical is quantities, and it can be continuous values like the temperature, or discrete, an age, a count of something, number of students in a study, for example. Categorical is going to represent different characteristics or qualities, and that can also be ordinal. So if I give a movie 4 stars, that's a better rating than 3 stars. There's a relationship between that. Versus nominal, so an apple, an orange, a banana, they're just different types of fruit. So these are the main types of data that we're going to run into. And it's important because remember we talked about all of these models are really mathematical models. So the categorical data, we're going to need to find a way to represent those as numbers at the end of the day before they feed into our model. And here's a summary, shows you the overlaps of those different types of data. At the bottom, I've shown what type of probability function is used for that. So probability density, when you have a continuous value, you can't predict like the exact temperature of 72.347 degrees. You would basically put it into a range of values. When you're doing any work in data science, machine learning, or AI, your data often takes the form of this matrix. So we call this tabular data, and you're going to have some number of samples or instances. So n instances here, and then each attribute or different piece of information, those are going to be your features. So we refer to this as an n by d matrix. So n being the number of rows in our matrix, d being the number of columns. An important assumption is that each of our samples or instances are independently drawn and they're random. So for example, we were going to predict height. We wouldn't want to pick 1,000 people all from the same town in the same state. We'd want to get a good mix. To make this more tangible, let's look at an actual data set. This data set here is from Kaggle. Kaggle is a website that has a lot of machine learning and AI type projects, and it's medical costs. So if we scroll down, we can see the data card, and this file contains information. It's got attributes, 6 attributes about people: age, gender, BMI, and then our target attribute is charges. We want to try to create a model to predict how much the insurance is going to have to pay out, what are the total charges going to be for this person based on this information. I went ahead and downloaded the data file, and we're going to look at it now in a Jupyter notebook. A notebook is a nice mechanism where you can both run Python code and also put notes using markup. Don't worry about it if you're not familiar with Python yet. We're going to cover that a little bit later in the course. For now, I just want to show you some information, because when you start out on a project, you're going to want to do some exploratory data analysis. That basically means let's find out a little bit about the data, see what it looks like, what type of distributions there are, what are the range of values, what information is in there. And then that'll give us more insight when we go to create our models and do other things with it. So here, I'm just gonna, each of these cells is a piece of code. So here, I'm just reading in that data file into what's called a data frame and just printing it out. So you can see these are the 6 features, and then the 7th target column is the charges. And you can see that there's 1,338 samples in there, so a good amount of data. And this gives you a feel. Again, we have some numeric data, we have categorical, whether the person is a smoker or not, and what region of the country they're from. Okay, we can also do a describe, and that's going to tell us some more information. It'll give us the average or the mean of each of these columns, and then you can see the different percentiles, the minimum and maximum value, give you a little bit of a sense of what's going on here. Okay, so charges is our target attribute. So let's look at the distribution of this. And so this chart here shows us that the distribution kind of looks like the exponential distribution that we looked at. And what's going on here, not surprisingly, there's a large majority of people that don't end up costing very much for the health insurance. They probably only go for a checkup, annual checkup. They're healthy, generally speaking. And then you get to a longer tail, and then you get some some people in the distribution have a large amount of charges. Unfortunately, they're not as well, and so they're going to the doctor more, things like that. So you get a sense of what are the values the range of values that we're trying to predict, and that informs us as we go forward. We can also look at the distribution of some of the other fields. So you see kind of some of the really one of each of the distributions we looked at. So age is spread across somewhat evenly. We have a few more folks that are around 20 years old, but it mostly looks like a uniform distribution. BMI, body mass index, so that is our normal distribution. So most people fall close to the average or the mean, and then it tapers off to either side. Number of children, so a good amount of households here that don't have any children, and then kind of tapers off as you go. And then we already looked at the distribution for the charges. Now, in exploratory data analysis, something you want to do is get a sense for, are there relationships between these different features? So a pair plot is a really valuable tool that you can use to kind of compare each field against another field and look for patterns. Okay, what we've got here is we've got a 4x4 grid. I did a pair plot of all of the numeric features against each other. And it's going to be, the columns on the X and the Y axis are going to be the same. So here you can see we've got age, BMI, children, and the charges plotted against themselves. Okay, so in a pair plot, the diagonal is the feature or the attribute plotted against itself. And so this is, once again, just the distribution. And when you look on either the upper right or the lower left corner, now you see 2 attributes compared to each other. And you can see visually at a glance if there's any kind of relationship here. So this first column is age. So age and BMI, you can see the data points are really scattered all over. There doesn't appear to be any real pattern there. Number of children and age, that also varies a lot. When you go down here in this lower left corner, okay, insurance charges against age. And so you can see there's this trend line that goes upwards. So that's not surprising. As people get older, they tend to go to the doctor more and may experience different issues. Likewise, in this BMI against charges, the pattern's not quite as clear, but you can kind of see, generally speaking, as you get a higher BMI, the charges amount does go up. So that could lead to having to visit the doctor more, other things like that. And then we also have a number of children against insurance charges. So it's interesting, the people with 4 or 5 children here, looks like many of them have low charges. So, we don't know at this point yet why some of these things are going on, but we can start to get a sense for what might be important features, meaning that which of these things are going to potentially impact our target variable and that we definitely want to include in our model. Now, when a pair plot compares or is plotting numeric values, if you're talking about categorical features, there's other ways that you can do that more effectively. So this here is a box plot. So this is insurance charges by gender. And the blue squares here represent between the 25th and the 75th percentile. And then you can see some outliers. So it looks like in our data, females have slightly lower insurance charges on average. Males have a little bit wider range for that middle 50%, but it also does trend higher. And then you can see where the outliers fall. So these are just some basic tools. This is a comparison of all of the different categorical attributes against each other. So this is part of exploratory data analysis, getting familiar with the data as we proceed. Now, we're not going to get into the actual models themselves for another module or so, but I just wanted to show you something that we can do with these, with this data rather. So I've imported some libraries from scikit-learn, which is a very common machine learning library in Python. And I've done a couple of things, some pre-processing. So I've converted those categorical features that we talked about. I converted those to numbers. We'll talk more about that later in the class. So that's what this pre-processing step is. And then train test split. What I've done is taken our 1,338 samples and randomly broken them out into 80% of them we're going to use to train a model, and then 20% we're going to use to then test and evaluate how we did. So I've actually created 2 models here, a linear regression and a decision tree. Again, don't worry the details. We're going to cover these in a later video. And then I've evaluated both of them. So it was interesting to see what happened. So for our linear regression, you can see here there's a couple of metrics. So MAE is the mean absolute error. That means on average, when we evaluated our test set, we were off when we predicted the insurance charges by about $4,000. The root mean squared error is a little bit higher. And our R squared score is 0.78, which means that you can interpret that as saying that the model accounts for a lot of the variance. 0.78 is pretty good. You'd like to see that over 0.8, but it's accounting for a lot of the variance that we see in the data. So our model's doing pretty well. And then I tried one other model, which was a decision tree, and you can see it actually did a little bit better. On average, it was only off by about $2,700 on its charges prediction, and its R squared score did go over 0.8. It's actually 0.86, so not too shabby. So you can see kind of what these different models, how they're going to perform. And we're going to talk about the total error. Where does this error come from, and what can we do to reduce it? And first, to clarify, what we're doing here is supervised learning. Our data has both the input features and the answer that we're looking for. So that insurance charges column is our target right here. When we were looking at the different aspects of the data, the distributions and the pair plot, we were performing exploratory data analysis. So we gathered our data, did some basic visualizations, and just looking for general patterns and relationships in there, getting a sense for which features might be valuable to use. That error we were looking at, every model has 3 sources of error that contribute to the total error. The first is bias. So bias would be your model is too simple. It's not complex enough to handle the nuances of the data or the scenario or the requirements. Variance would be if I took a different set of 1,000 people and used their data, how much in insurance charges they incurred, I would get a slightly different result or a very different result. We don't know. So the sensitivity to what data you train on would be related to variance. And you can see in these bullseye diagrams here on the right side, you can see the impact of the difference. And you often hear of bias, variance trade-off. So sometimes when you make your models more complex, then they overfit to the training data, but they don't do as well when you give it other unseen samples. But ideally, we want, in a perfect world, low bias and low variance, and that would be in the upper left corner here where we're hitting the bullseye on every mark. When you have variance, you see a scattering of different point estimates. And then on the lower right, if you have low variance but a higher bias, your predictions are closer together, but they're off by some systemic amount because your model is not quite fitting the problem very well. Finally, you have irreducible error, meaning that the real world just has variations that we can't account for. It could be due to probability, it could be due to differences, it could be that there are features that influence the outcome that we don't even have data on. So there's always going to be some amount of irreducible error that we have to live with. But that's where, when we were off by $2,700, that 2,700 is broken down. It's comprised of elements of these three aspects right here. Okay, one last topic. So correlation versus causation. If you see a correlation between attributes, there's a statistical relationship there, but that doesn't necessarily mean that one caused the other. You would need to do more analysis. You probably need human experts to figure out the actual why of what's going on. So a canonical example is this diagram here. So on a hot sunny day, you might see people get more sunburn and also eat ice cream. Now, does getting sunburn cause people to eat ice cream? No. The sun, the hot sunny day, is what's causing the sunburn. It's also causing heat and having people want to go eat ice cream. So you see a correlation between sunburn and ice cream consumption, but that's not necessarily a causal relationship. And so keep in mind that a lot of machine learning models are based on correlation. They're looking for statistical relationships because that's really what they know. You would need human expertise or other mechanisms to try to add more causal information. Now, with that said, they're often correct. But this gets into an explainable AI topic. Why do models come up with the answers that they do? Why does ChatGPT answer you the way that it does? So we're going to dig into those topics a little bit more further in this class. Let me leave you with one last thought on the correlation. And this is important when we look at AI systems and machine learning models because they do have potential biases in their data or other issues. And it's important to know how they're actually working. In this study, this is from a research paper a number of years ago. And this paper it analyzed a system that was classifying images and categorizing them as either huskies or dogs or wolves. And so if you look on the left side here under the lime heading, here it's highlighting the aspects, really the pixels of the picture, the regions of the picture that influence the model's decision. And as you can see in the husky picture, what it actually determined was it actually used the snow in the background as the important classifying part, or I should say the part of the image that most heavily influenced the decision. So clearly, if you're trying to actually categorize an animal, the background is not what you want to use. So that's why it's important to look at what's actually going on in these models and understand that difference between correlation, causation, make sure the systems are performing correctly, and that's how you can eliminate issues like bias and things like this. So I'm going to leave it there. I will catch you in the next video.